Hello boys and girls, welcome to another video on our YouTube channel. My name's Craig, I'll be your host in this vlog where I talk about beer and do something with electronics. Today something different. I'm trying out OBS Studio, so you can see me in the little bottom right hand corner. We're going to continue with our design series. This came about from a colleague. As you may be aware, in South Africa our power utility is broken. So everybody's putting in solar panels and battery backup and all sorts of funny things. The issue with that is it's relatively expensive in South Africa, and I'm not going to bother with doing the maths on cost to return. We're putting it in to get away from the grid. It is a luxury, and that's what it is. The circuit we're going to actually design from scratch is a request from a colleague, a friend of mine. He's put in a solar system. It's a little bit on the thin side, and what happens, Eskom's power goes out and his wife may switch on the kettle, which will have a draw on the batteries. She may use the hairdryer or whatever, but at that time the geyser will kick in. So the circuit what we're going to design is basically a power monitor. We want to monitor the state of the battery bank, and depending where that is, we will disable the geyser, and we'd also like to monitor a few other things. So I'm not going to waste time. We've got the schematic open, a blank canvas. Just got to move over to that. Out of curiosity today, I've got this Cederberg Brewery Footsack Indian Pale Ale, crafted by David Nivoud and Alex Nell, brewed with pure mountain water filtered through sandstone. I don't know a lot about Cederberg Brewery. I think it was two sisters that actually opened it. I may be wrong, so I'm going to get our beer in. And let's move straight over to our canvas here. So if it looks like I'm not looking at you, it's because I'm looking at the screen behind my laptop. I'm sitting at my workbench, and it's just the way it is. The first thing that I would like to put in here, I'm using KiCad or KiCad. It works for me. It's free. The component or part list is pretty updated. They have a partnership with DigiKey as far as I understand. So I'm not going to teach you how to use KiCad. I'm just going to select on bits. So it's free. It's easy to create the schematic. So first time I'm using it on this project. So it's got to build its symbol library and everything. I would like to have some terminals. Screw terminal, doesn't matter. I'm going to go with a 3 terminal because I'm going to have AC mains coming in here. I'm going to have live, neutral, and earth. The next thing I'd like to do is have a switch. What type of switch would I like? I like a double pole, so it's got to have 2 poles, double throw. No, I want double pole, double throw. I did type in, yeah. Okay, let's try switch. Come down. Polyfuse, no. I don't want any of this cock. No. Maybe we'll find something here. During my package, funny. Oh, yeah, me being stupid. It's not double pole, double throw, it's double pole, single throw. Now, we're going to come off mains to power our monitoring circuit, so we're going to need some sort of protection here, so let's go for a fuse. We won't worry about the to rotate it. I'm just pressing R. We're not going to worry about the ratings now. We're going to put everything in that we need, and then we'll come back and align it. If you don't mind, I do smoke, so I'm lighting a cigarette. I haven't even had a sip of beer yet. Okay. Very malty. I would like some, so I've got a fuse, but I want something to protect us against transient noise. So our raw power from our power supply, especially South Africa, is not great. There is transient noise in, and transient noise, we know our AC wave flows along at 50 hertz, and it's got a amplitude of 230 volts. The problem is sometimes we have spikes in that noise, and that damages our electricity. So, components. I'm going to put in. We don't have that varistor. I'm going to put in a voltage-dependent resistor. We call it MOV, metal oxide varistor. I'm going to put in 3 of them. I'm going to go between line and neutral. I'm going to go between live and ground, and neutral and ground. What this thing does, as the name says, it is a voltage dependent resistor, so that depending on the rating of the MOV, if the voltage is below the MOV's rating, the MOV has got a very high resistance. If the voltage goes higher than that, then this thing becomes like a short. It starts conducting very well. To copy them, I'm just pressing C. Okay, so now we've got our terminals for input, we've got our switch to isolate it. Just want to get rid of that. Single throw, double pole, single throw. What I would do is go back and put, no man, what am I doing that? Phoenix, because I want Phoenix, but I want, we'll go back to that. We'll move this across. So what we're doing, by putting these MOVs here, we're saying, hang on, if this voltage starts going out of whack, we can create a direct short to ground, to neutral, and we can blow the fuse. So we've protected our circuit. We're going to need a bit of a transformer because we're dealing with mains, and I don't want mains for where we're going. So let's see. Transformer, 1 primary, 1 secondary. That looks good enough for me. Let's get our thing, our pointer. Well, I want 230 volt AC. What are we going to step it down to? I'm going to go with 18 volts AC. I'm going to put XVA for our power because we don't know how much power we need yet. Volts will work well for what we're trying to do. I'm going to do this this first part. I'm going to do it very old school. So I'm going to use components that you would find typically, that you would have, if you're into electronics, you would have lying around. And we're going to do two variations on this. We're going to do a modern variation, and we're going to do an old school variation. We'll do an old school variation where we use op amps, comparators, and things like that to do what we want, and relays. And we'll do a new school variation where let's use a microcontroller and LCD, and we'll make it very smart. Okay, so we've got a transformer, so what we should start doing is connecting these things up. Why? Okay. Let's rotate that. One thing we're missing is we need a protective earth. So we're going to have a normal digital ground. Yeah, let's have a digital ground. We'll put that there. And we need a protective ground. I don't like the symbols. Okay, we'll use the protective symbol. Normally I prefer this of it to show that the chassis is earth, but okay, if they want to use this, it's fine. Right, so what we do know is we're going to take our live, our neutral, and our earth. Live and neutral we're going to take to a switch. The earth we're going to take straight to the chassis of our box. So our box, I don't know what we're going to use. We're going to probably use polycarbonate, which is not a train smash. 1, 2, 3. The 3, it's just, I like it because it's sort of evenly spaced and it works for me. Our fuse, we're going to come 1, 2, 3. Actually, we're going to come more than that, but anyway. Let's move our varistor. 1, 2, 3. So that means 1, 2, 3. Okay, so we're going to have 1, 2, 3. We'll have our mark between live and neutral. So if we have a transient surge, this will short, blow that fuse and go back. Let's have one between one, two, and the same thing here, we'll move it. So if we extend our lines, let's see, we bring our transformer here. Let's move these over. So we have a MOV from live, and we have a MOV from neutral. We have our transformer primary. Let's say 1, 2, 3. And they are going to short to earth. So that takes care of our protection on the primary side. Yes, I'm using a transformer, so I'm using a linear power supply. But what we've created, or what we've taken care of here, is we've got our earthing, we've got our supply, we can isolate our supply, and if for whatever reason there's transient noise, oh, I don't like that, that hasn't got the spacing, so I want to move that over. Yes, so if we have transient noise, or voltage surges from our power supply company, these devices will come into play, and they will short, they'll blow the fuse. Worst case scenario, if we bugger up our fuse rating, they will still short, but we will trip our isolator and our DB board. But clearly we don't want to do that, we would like to size these properly. Okay, so that takes care pretty much of our AC side for a linear system, a linear power supply. Now we need to do a few things. We need, obviously we don't want to be working with AC, so we want a bridge rectifier, bridge. Clearly I can spell today. Diode bridge. No man, don't you have a decent looking diode bridge? VAC. Oh no, I don't want. I can rotate the thing. Can I? I mean, there's got to be a better. VAC. Okay, let's see what this one looks like. No. Where is my delete? I mean, there's got to be a better looking diode bridge than this. They're all looking like this. Okay. Orientation, rotate clockwise, there we go. Okay, before we put our diode bridge in, no, I'll do it on the DC side. 2, 3. Two, 3. Clearly I didn't do that on this 3. Oh, I did do this 3, it didn't come out nice. Right, there we get our positive and negative runs. So, we've now rectified this, but if you remember, it's going to look like that. So let's put a bit of a bulk storage capacity in here. And anyway, okay, we can have a polarized capacitor. Again, we don't know how much we need, so I'm going to leave it for now. The problem now is we've got 18 volts on the other side. That is going to give us a peak value of about 26-25 volts off the top of my head. So what we need to do is we need to step this down. Remember we said we want 18 volts, so what I'm going to do is I'm going to use things I have at home. So I'm going to use an LM317, which is a programmable voltage regulator. Nothing very fancy. It's got an input, an output, and an adjustment, and it's actually a very simple device. You set this thing up. It's just draw it like this. Okay, we'll just give me R. Okay, fair enough. Oh, that's not nice. It didn't line up very well. set this device up is actually very simple. We've got two resistors. This adjust pin, so whatever voltage we're targeting out here, this adjust pin wants to be 1.25 volts less than that adjust pin. So that gives us a pretty simple voltage divider. Of course, we'll look at the data sheets and we'll come back to it, but it makes it very easy for us to program this thing. How are you doing that? That will go to ground. So by setting this voltage divider network, we can program whatever voltage we want on the output. And then 317. Sorry, I don't like all these huge fields in here, so yeah, again, by programming this voltage divider network, if we know we want 5 volts out here, for example, or 18 volts, 18 minus the 1.25, divided by this, or in our case, we don't know what these resistors are going to be, but we know we need a certain current in here, and typically it's 50 microamp. If we took 18 less the 1.25 that this thing wants to see below that, it will give us our whole setup. So 18 divided by the 50 microohm will give us the voltage combo multiplied by the 1.25, and then obviously subtracted by whatever else. Then we can adjust these resistors. I'm not going to do it. Well, no, I'm not going to do it now. We need to do a few more things to make this regulator a bit more stable. What I want to do is put a capacitor. Let's put another polarized capacitor here. Actually, let's move it in line with that one. So if we put a polarized capacitor here, to ground, all we're doing is we're making that voltage there a little bit more stable. So whatever noise happens in these resistors and in this circuit, this voltage capacitors are going to absorb those voltage fluctuations, and we will have a stable voltage there. At the same time, I think let's put a capacitor on the input for that device. One more thing that we can do for this LM317, I'm going to put in this 5819. I'm going to put a diode in here. Well, in this case, it's a Schottky. You didn't have to use a Schottky. I'm using a Schottky because I have it. If for whatever reason they short the output of this, well, this diode will clamp it. It will also give it a path for the capacitor, this capacitor, to discharge. So I think that's what we need for I think let's put also we'll copy that, we'll put one more bulk storage capacitor. Alright, that allows us to fix this side up. Yes, I know a lot of this is making it look pretty, but if you're doing drawings, you really want to try and make them readable and in a way that they flow. Okay, so that gives me our first voltage regulation circuit. And what I like to do, besides saving it, is I like to put in little text notes to remind me what I'm doing. So I'm going to say 18 V DC regulator. So now we know whatever's happening here, because remember this 18 volts is not going to be really 18 volts. DC, it's going to be quite a bit higher, especially if our transformer is not loaded. Then that means my LM317 will have the headroom that it needs to step down the voltage. I just want to get rid of this text. I don't like, it's the cuckest thing I don't. I'm just going to call it P number for myself, because I like to put the part numbers instead of this description like Varus, that I would actually go and put the part number in, but we will come back and we will do that. So now we've got an 18 volt DC regulator. We've done the AC side, we've protected it, we've got the DC side, and we've put in a regulator. We need to look at the criteria that my mate has for his circuit. So we know our batteries. "56 volts DC." Let's actually do it like this. Is full. "44 volt DC empty." Now these are the figures he's given me. I couldn't be bothered to go work it out. Basically what they're saying is if his battery bank is at 56 volt DC, he's happy, the things are fully charged. At 44 volt DC, they are basically half, or whatever the criteria is for the minimum charge, or do not discharge below this point. So we need to measure this 56 volt DC, which would be full, plus some headroom for safety, as well as, well, 44, we don't care about low end, we might as well just go 0 to 56. But we've just regulated our circuit to 18 volts, and we know a lot of our ICs are not going to work at 56 volts. So we need to bring that power down, that voltage. We need to drop it. And I don't, well, the easiest way to do it is like, let's put that note up there. We'll leave that part of the circuit up there. Let's put in from our batteries, and so because we've got again, I don't like that. Let's just call it Phoenix, because that's who I will get my terminals from. I don't have an affiliation with Phoenix. I do use their stuff in the real world, in the professional life. They've given me some very great service in the CNI world. If you're looking for converters and stuff, I do like their terminals, especially their PTT terminal range. The cage clamps, most excellent stuff. Okay. What I'm going to need, because we know our batteries are going to give us 56 volts. I need some sort of voltage divider string. Don't worry, we can always come back and make this neat. What I didn't put in is I didn't put our ground in. Now might be a good time. Notice that ground and that ground are isolated by this transformer. They do not meet. Okay, very important. So yeah, I've created a voltage divider. What does that help? So we have a reference point. How about in the electronics world, there's a very, very cheap chip. It's probably, if Legend has anything to do with it, it's probably one of the first integrated circuits ever invented. It is magic. I use it to this day in all sorts of applications. I'm going to put in an LM741, an operational amplifier, and I'm deliberately using this chip. The LM741 is an operational amplifier with, let's see if I can get the data sheet to play with. No, what am I doing? Either way, the LM741, I will read the data sheet to you. It's got overload protection on the input and output, no latch up when the common mode range is exceeded. Applications, comparators, multi-vibrators, DC amplifiers, summing amplifiers, integrators, or differentiators, active filters. The easy way to understand this thing is to know this output let's move it. I'm going to give it little labels here. Out, in, wait, let's call this II, out. God, why are you doing this to me? NI, out. Why am I calling it this? Unfortunately, these guys labeled these pins, and this is a standard, as plus and minus, but what it is that is the non-inverting input. The minus is the inverting input. The out is out. Now the magic with an op amp, if we talk about an ideal op amp, this has infinite input impedance. In other words, the resistance here is infinite. There is no current flowing in to that input. The same with that input. The op amp output has zero impedance. In other words, there is no resistance on the output. The next thing that is important about an op amp is the gain, because we can use this thing as an amplifier, is infinite. So if I could put 1,000,000 volts on this supply, that supply, the op amp has got no problem. Its gain is infinite. It can go. You can amplify. In other words, you could amplify a signal here from 0.01 or 10 millivolts or 1 millivolt to 1,000,000 volts. The gain is infinite. Obviously, in reality, this is not going to happen. But to understand op amp, you should adopt that the gain is infinite. An op amp is a very versatile little animal. This output, if we put power here on 7 and 4, the output will do whatever it needs to do to make these two inputs equal. And this becomes fairly good in control theory because we use things like feedback, so we would take the output back to one of the legs and through whatever. But if there is no feedback, the output is going to keep going whichever way, up or down, to make these two inputs equal. How does this help us? Well, how about if we use this thing as a comparator? How about we gave this leg let's give it a, I'm just going to put a text here. If we gave this thing a reference of whatever, reference voltage, okay, as long as this non-inverting leg is below the reference voltage, the inverting input, this output is going to be high. It's going to be up, close to whatever that rail voltage is. Remember we said 18 volts, so let's draw that in to make it easier to understand. Let's copy, where is our... and let's put our little label in. So remember we said we're going to drive this thing to whatever the rail voltage is, or whatever. So if, for example, this reference voltage was at whatever we decided to scale it down to, maybe 4 volts, 5 volts, as long as this non-inverting input is below that 5 volts, so let's call that reference voltage 5V. If this input is below 5 volts, that output is going to be 18 volts. In reality it won't, because op-amp has a thing called rail-to-rail voltage which it can't handle, so, but it will be close enough to 18 volts. I think in our case, LM741, it'll be 1.5 volts below that. So, as long as this input is low, that output is going to be high. In other words, this input is below that reference of 5 volts. Bang, up we go. The output will be high. As this voltage rises with whatever we're trying to do, and it meets this reference voltage, the output will start becoming low. Because we're using this as a comparator, this is going to happen relatively quickly. This is below the 5 volts, high, bang. This meets the 5 volts or goes lower, bang, we switch off. So we've effectively used the op-amp as a comparator. Very important for what we want to do, because think of it, if we took our battery, so let's make a nice little text here. Battery in 46 to, I'm going to make it 42 to, no, 46 to 56 VDC. If we were somehow to set up uh, 44, if we were to set up this battery or this voltage divider here, that somehow it was in relation to that. In other words, maybe we could drop it by a factor of 10 or 20 or whatever. Effectively, if it was 44 here, we'd be getting 4.4 here. If it was 56 here, we'd be getting 56 here. And that is the magic of this. So we could use this resistive divider, and if we brought up our whole circuit like that, and we took that input into there, well, hang on, we've got a reference, we've got something that can do something here. Aha, so we can use this op-amp to measure what's going on against something that it knows, and do something with it. Maybe we use it to drive a transistor, relay, a switch, or whatever. And we can now monitor this battery voltage and with this output we can say, right, okay, we don't want your geyser on, we don't want your kettle on, we don't want whatever. Again, remember, think of the op-amp. In reality, it's not ideal. There's nothing in the world that is ideal. But no current flows in there, so that voltage, there's no volt drop. The op-amp will try to do whatever it can to make the two inputs equal. Whichever way must go, depending which is higher, must go up, must go down, it will drive whatever way to make it equal. It will try to drive to the rail voltage. In this case it's 18 to ground, but normally in op-amp it'll be plus 18, minus 18 or whatever. So it will go to whichever rail that is there. And the other thing with the op-amp is it's got infinite gain. I could take, I'm not going to go into it in this video, but if I took a resistor from there, put another resistor there and in there, or resistor whichever way, I could work out an amplification factor, and we will get to that in this series. Excuse me. But our op-amp has infinite gain. I could have a million volts here, and my gain, I could amplify a 1 millivolt to 1 million volt output signal. Unfortunately, in the real world, it doesn't work like that. But when you're analyzing an op-amp, you have to understand it has those sort of things. So I'm going to leave the video here. I just want to recap. We said we're going to have obviously terminals to come into our circuit. We're going to have a little bit of an isolation. We've got our protective earth. We've got our fuse to protect our circuit. We've got 3 little components in that we said if we have transient voltage or over voltage or whatever, these things will become shorts. That will, because they become shorts, they draw enough current, they will blow that fuse. We don't really want to work with mains voltage in our circuit. Our components need a little bit less. So we decided we'll go from 230 volt mains in South Africa down to 18 volts. We don't know how much power we need, which is just the voltage times the current. So we don't know how much current our circuit's going to pull yet, but we'll get there. We'll back calculate it. We said we're going to rectify it. In other words, we don't want a sine wave, we want a DC wave or inverted sine wave. We rectify it. We'll smooth out that ripple. We said we put in a little LM317 programmable voltage regulator. We'll give it a bit of bulk storage up front. We program the output voltage regardless of the input voltage based on this voltage divided between those two resistors, bearing in mind that this voltage must be 1.25 volt below that below that voltage. That's what this regulator wants. We put it in a little bit of a smoothing capacitor here, just to keep this voltage constant, so whatever noise, whatever's happening here, this capacitor can absorb it. And the last thing we put in is we put in a discharge path for that capacitor in case of a short, so they can discharge whatever. And then on the output we just put in a little bit of a smoothing capacitor, a little bit of storage smoothing capacitor again. So I'm going to call it I'm going to call it a video on this stage. What we'll do is we'll come back in part 2 and we'll work a bit more around this, the op-amp, and what we're going to do and how we're going to achieve the goal of monitoring and switching as my colleague requires. Anyway, the beer, not much hop aroma. It's very malty. For you guys, did they even tell me? Yeah, okay. 6% alcohol. There's a bit of stuff on the side, it's in Afrikaans. Basically what they're saying, legend in die omgewing, so a legend in the region. What? Okay, together they lived, together they survived, and together they celebrated, and together they died. Pure mountain water from the Cederberg wilderness area, naturally filtered through layers of sandstone, gives this epic beer its signature taste. A brew of skill and passion, preserved by hops only. Pleasantly hoppy with floral and citrus aromas with a brilliant dry finish. A full flavoured beer for the hop lovers. I don't know, sorry. All I get is malt. Yeah, not a malt. Not hops. Not a bad beer, but no hops. Anyway, as always, until next time, take care, be safe. We'll catch you in the next one. Cheers.